generic vector space to discuss. So, last week we have given a theorem, theorem 2.4.3, to describe a simple way to check whether a function from a vector space to another vector space as a linear transformation. Okay. And further, I would like to make a couple of remarks. So the first one is, so we let T from this to W linear okay, and V and W are vector spaces. Okay. So the first thing is, if we transform the zero vector in the vector space V, then the value would be the zero vector W. Okay, and so the short proof is here. Right. So the zero vector can be expressed as zero, scalar multiplied with the zero vector V here, and by the linearity of the linear transformation T, so that would be here, the zero times T. Now, no matter what is T of zero V is, but when you multiply with the scalar zero, then that would be zero W. Okay? And if you want me to indicate which theorem I have used, maybe see it. Okay, so this is by theorem 2.4.4, and by linearity of T, and this one is again by theorem 2.4.4. Okay, so that is the first remark. The second remark is that for any V1 up to Vn in V alpha 1 up to alpha n are the image of the linear combination of linear combination of V1 up to Vn is that by association, so we can think about that. This is one. Okay. And so there will be one here. Okay. And that would use axiom. Two and 7. Okay, so here I use the unitary property, and I also use axiom 2. Axiom 2 is about the also the activity of vector addition. Okay. And by linearity, okay, so I apply the linearity. Okay, by the linearity side. Okay, and again by unitary. Again, by the unitary property axiom 7, we have this rule. So, starting from here, the image of linear combination of n vectors in capital V, we have becomes to the sum of the image of the first n minus 1 vectors, V1 up to Vn minus 1, such a linear combination. And but we have alpha n multiplied with the image of Vn. So we can do that recursively. Okay, so we can do that recursively and end up with T V1. Okay. Any questions? So you can think about this is a general version of the linearity of T. Okay, and so I will prove the following theorem. So later U1, U2 up to Un be a linearly independent set. And then the subset of a vector space V, and we have V equal to the span of this subset. Right, so we assume V is a vector space, and we can find a linearly independent subset. This subset consists of n vectors, and also find that the whole vector space is the span of this subset. Okay. Next one, relate V1 relate W with W of 1 of 2 up to Wn, the arbitrary vectors in a vector space W. So now probably another vector space W, we pick up n vectors arbitrarily. Okay? Arbitrarily, okay? Now Okay, then the conclusion is that there is a unique linear transformation T from V to W, okay, such that T Ui equal to Wi for all I in 1 to n. Alright, so the theorem gives us a way to construct a linear transformation. And the thing is that the consumption is that this consumption is unique. Once we have one, then this linear transformation must be unique. So we have to know the premises. The first one is that in the domain V, we are able to find a linearly independent subset U1, U1 such that this subset spans the whole vector space. This is one premise. The second is that in the codomain W here, we can pick up n vectors arbitrarily, so that we can let the Wi be the image of Ui. So this is the specification, the spec we want. So usually we are interested in such an assignment, just assign image for certain number of vectors in the domain. But for such a linear transformation to be exist and unique, we have to know that U1 up to U1 is a linearly independent set and also expand the vector space between. Okay, so let me give you a proof. First of all, we will use the first assumption here that this subset is linearly independent and also span the whole vector space. And we have a closely related theorem before. That is theorem 2.4.6. 2.4.6, by this theorem, each vector U is vector U in V, and we know V is the span of U1, U2 up to Un. Okay? So for each vector has a unique representation as a linear combination of U1, U2, up to each vector in V can be represented as a linear combination of U1, U2 because that the V is the span. So each U is in its span. But this representation is unique is because U1, U2, UN is a linearly independent set. Okay? So you have to know. Uniqueness comes from linear independency of this subset. Okay, that is the crucial point of theorem 4.6. Right, so so that the U can be expressed as A1 plus A2, plus AN, Okay, so this representation is unique. And because it's unique, so we define. Now we create. We define a function t from v to w as, okay, so for each u, okay, when we represent u as a unique linear combination, because this is unique, okay, so that then tu will be defined to be a1 w1 plus a2 w2 plus plus an w. So the image of u becomes to a linear combination of the w1, w2 up to wn in w. Okay, but we copy the coefficients here. Just copy it. Alright, so this definition is well defined because it's a function. Well defined. Because there is no ambiguity about the coefficients. Okay? Because of the uniqueness of representation. So different u will have different a1, a2 up to an. Right, so they will have different set of coefficients. Okay, so now, so we can establish a function. But what we want is a linear transformation. So we have to check that this is a linear transformation and satisfy this requirement. So first of all, we will check things. UI, okay. UI has a unique representation, right? So 0 U1 plus 0 UI minus 1 plus 1 UI plus 0 UI plus 1 plus 0 U and here. So the T UI is 0 W1 plus 0 WI minus 1 plus 1 WI plus 0 WI plus 1 plus 0 WI by our definition of T. And so this is just WI. Because 0 times I out, there are 0 vectors in W by theorem 2.4.4. Alright, and the one by the unitary extent, we have WI. Okay, so we have, so this is for all. Alright, so the mapping, the requirement is satisfied. Okay. Alright. Now also for W, also for V equal to V1, U1 plus V2, U2 plus Vn, Un. V and alpha in R, we first look at U plus V. Okay, so when we add U plus V. U is here, right? And the V is another vector in the capital V. So vector U and the vector V, their sum is A1 plus B1, A2 plus B2, plus AN plus BN. Okay, so we can apply the axiom of commutativity about the addition, the axiom of associativity about the vector addition, and as well as the distributive laws, okay, about scalar multiplication. So actually you can sum up with this one. And for alpha U, this becomes to alpha A1 plus alpha A2 plus alpha AN. Okay, so the multiplication, scalar multiplication of alpha and U comes to this linear combination. So as linear combinations of U1, U2 up to UN, they are unique. Okay. And so by definition, TU plus 3. By definition, that would be A1 plus B1, W1, A2 plus B2, W2, plus AN plus BN, W, and yeah. So we have that. As definition. Yeah. Alright, so now this is a linear combination of vectors in capital W. Right? So and now we can split them into by the 7 axioms. Okay, so by the 7 axioms, we can split them into the sum of 2 vectors in W. And this is exactly the definition of the U plus P of V. Okay? Alright, so we prove that the image of the sum of 2 vectors U and V in capital V becomes to the sum of the images of vector U and vector V. Similarly, the image of alpha U by the definition of T becomes alpha A1 plus 1 plus here. Okay, and apply the 7 axioms. Okay? And this is alpha TU. So now with these two results, so by theorem 2.4.C, we just proved last week, T is a linear transformation. Okay, so now the existence of a linear transformation with this property is not justified by the construction. Right? So actually we by the construction. So the final thing is to prove the uniqueness. Okay, so let x equal to w be another linear transformation. Okay, such that s ui is equal to wi for I from 1 to n. Okay, so suppose we have another linear transformation satisfy our specification. Then we need to show that this function x is actually equal to the function t. Okay, now then for all u in 3, okay? Now SU. So SU is SA1, U1 plus A2, U2 plus. Okay? And by linearity of from our remarks at the beginning of the class that we have this one, and because as ui equal to wi, so it's 1 plus a2 plus 2 plus here. Okay, because we have this specification. But indeed, this is by our definition of T, this is indeed TU. And we have done. So that T is unique. Immediate. Because we prove that for each vector U in the vector space, the two images are equal. Okay? So that S and T are the same functions. Okay. Any questions? Alright, so the last theorem for section 2.4 will be theorem 2.4.13. So let P be a linear transformation. Okay, and of course, V and W are vector spaces. Now, if the index set U1, U2 up to UM is linearly dependent. In V, then the index set T U1, T, U2, up to T, Un is also linearly dependent. Okay, so this theorem says that for any linear transformation T, it will map a linearly dependent set into a linearly dependent set. The proof. The index set U1, U2 up to Um is linearly dependent in V, even only if there exists alpha 1, alpha 2, up to alpha m, not all zeros, such that alpha 1, U1 plus alpha 2, U2 plus plus alpha m, Um equal to the zero vector. Okay? So this is a definition of linear dependency. Okay, so now we apply T on both sides. Okay. So we apply T on both sides. The right-hand side, of course, is zero vector. If you like, you can. Sorry. You may say that this is the zero vector in capital V. This is the zero vector in W. Anyway, and the left-hand side will be. Right. So now the left-hand side is a linear combination, and the coefficients are not all zeros. So the whole thing, which is a non-trivial linear relation. The index set. Okay, so it's a non-trivial linear relation. So that U1, U2 up to Um is linearly dependent. Okay. So the proof is easy. Okay, so this is the end of section 2.4. All right, so I would like to proceed to chapter 3, and the first section is about matrices, and we know a lot about matrices, so that I just make a comment. So we have discussed a lot about matrices. Okay, in the class lecture. Especially in chapter 1. Okay, so please read. Section 3.1 of the textbook. As homework. Alright, so now I will go to the second section. It's about matrix inverses. We talk about matrix inverses in chapter 1 when we deal with Gaussian elimination, right? Talk about elementary matrices. So this section gives us an opportunity to further investigate the inversion of matrices, not only the square matrices, but also rectangular matrices. All right. Okay, so first of all, give a definition. All right, about rectangular matrices. So let A, B, and N times N matrix. And B and N times N matrix. Okay? So A N times N, B N times N. Different, okay? In general, when N and M are different. So A and B, if N and M are different, then they are rectangular matrices, not square matrices, okay? All right, a situation occurs sometimes when A multiplied with B is the identity matrix. So let me give the dimension of the identity matrix. A is M times N, right? B is N times N. So the identity matrix is M times N. Okay? So when we have this result, then A is called a left inverse of B. And B is called a right inverse of A. Okay, so left right just depends on their positions, right? So, but this is true. A is called a left inverse of B, and at the same time, B is called a right inverse of A. And I use a indefinite. It's not definite, okay? So that means that probably we have another left inverse or another right inverse. Okay. Any questions about the definition here? Before going further, we take an example. Suppose A is 2 times 3 Alright? So this 2 times 3, and B is 3 times 2. Okay? Now we multiply A and B together. Okay? And we find that this is the identity 2 by 2 identity matrix. Right from this particular example, so you can see that this matrix A is a left inverse of matrix B. On the other hand, matrix B is a right inverse of matrix A. Okay, so you can construct many examples. Okay. Right, so the first theorem, if an M times n matrix A, because once we have a new concept, we would like to relate this new concept with all the concepts learned before, right? We want to know new concept has any influence on what we learned up to now. Okay. So now, if an M times a matrix A has a left inverse, say C, left inverse, so left inverse is N times M. Okay? i.e., we have CA equal to N times N identity matrix. Suppose we have this situation, then any linear system AX equal to B with B in Rm. Rm, yes. Okay. Has at the most one solution. So the inference is now here that if we know the coefficient matrix A has a left inverse, say C here, then any such a linear system, we can put the B, right, from Rm arbitrarily, right? For each B, you have a linear system, right? But no matter what kind of B you put here, such a linear system has at the most one solution. So at the most one means either no solution, or there's only one and only one solution. So it's a crucial influence, right? Because the only information we know is that the coefficient matrix A has a left inverse. Okay? So the proof. First of all, if AX equal to B for B in R is inconsistent, right? So the first situation is that the linear system is inconsistent. Then there is no solution. Okay, so no solution still satisfies the conclusion, right? And the most one, right? No solution is also less than or equal to 1. So it's fine. So the first case is fine. Right? The second case is that if the linear system for V in Rm is consistent, right? It's consistent. It means that there is at least one solution. Okay? So you can solve the linear system. So we have only two solutions. Either the linear system is inconsistent or consistent. If it is inconsistent, there is no solution at all. That's fine. Our conclusion is still valid. So now we have to deal with the second situation, that the linear system is consistent. Okay, so now we have a solution, right? So then we apply C on both sides. Okay, and by the associativity of matrix multiplication, we can do the multiplication C and A first, so that this plus I and equal to CB, so this is equal to X. So X must be C times B, 1 plus B, so it's unique. Okay, so there is no other solutions, just this solution, one solution. Okay. So the result in theorem 3.2.1 is easy. Okay, it's easy. Now the next supplementary theorem is more delicate. 3.2.8. Okay. And M times N matrix A has a left inverse. Okay? Even only now, the existence of a left inverse of a rectangular matrix depends on A itself. Of course, that will be the intrinsic property of the matrix A. But what is the exact intrinsic property? We have to point out. Is that the kernel of A should be trivial. Okay, so this is the only condition. So the connection of the existence of a left inverse of a rectangular matrix is exactly to see if the kernel of A is trivial or not. Okay, so let me. All right. I think a better strategy is to give you a break, right? Now. Okay. So we'll have a break up to 11 o'clock. Okay, so it's consistent. And so, by our theorem here, because A has a left inverse, right? So that any linear system has at the most one solution. And this one has at least a solution which is 0. So that means that X is 0 by the theorem 3.2.1. Right? So any vector in the kernel of A must be equal to the 0 vector. So kernel of A consists of only 0 vectors. Right? So we have done. This is easy part. Very easy, right? Now the difficult part is the inverse part. So before to provide a proof, I will give you the idea behind the proof. Okay. So the idea is that to find. So our way is that given this condition, we want to find a left inverse. So we want to find by construction. This way, I will do it directly, meaning to construct a left inverse directly. Okay, so now we have to know, but to construct such an inverse, the left inverse, what can we do? How do we use the tools we learned up to now? Right, from chapter 1, chapter 2. Okay. So to find n times n matrix C, okay, such that CA is equal to the identity matrix, i.e. So to find this, alright, and so now C is unknown, right? Now C, the left inverse will be unknown, and the A is known. So with our experience in chapter 1 to solve linear systems, we transpose both sides, right? So that this is the same as the CA, we transpose them. We do the transpose. Okay. And which is, and this is A, P, C, P equal to identity. Because the transpose of the identity matrix is also the identity matrix. Alright, so now it's AP, CP. So now we have unknown here. This is unknown, and A transpose is known. Okay, and so now, so to find left inverse, we come to find a solution for A, P, x1, x2 up to xn equal to e1, e2 up to xn. So basically we have n linear systems. Right? So this consists of n linear systems. Because A transpose x1 equal to e1, A transpose x2 equal to e2, and A transpose times xn equal to e. They are standard unit vectors. Okay? We know that before, right? So they are standard unit vectors. Okay? They are n. Okay? Because the identity matrix has n columns, and this n column just standard unit vector. For example, E1 is 1, 0, 0, 0, 0, right? E2 is 0, 1, 0, 0, 0, 0. And the En is 0, 0, 0, 0, and the last is 1. So, i.e., we have to find A transpose xi equal to ei for I from 1 to n. So if we can solve this equation, then we find a left inverse. So that is the idea. All right. So now our focus is to solve this equation using the technique we learned up to chapter 2. Any questions about the plot, the idea behind the proof? Any questions? All right. Seems no questions. I would say. All right. So what we have is that kernel is trivial. So now since the kernel of A here, okay, the only solution of the homogeneous linear system Ax equal to 0 is x equal to 0. Okay, so which means that the columns of A A1, A2 up to An, the columns of A are linear independent. Okay, so we know this many times, right? We encounter this situation many times. This is because that it can be written as x1, a1 plus x2. Right? So this product, matrix A times a column vector, can be expressed as a linear combination of the columns of A, and the coefficients are from the vector A squared. And we know that this is just a linear relation, right? This is a linear relation on the column vectors of A. And because the homogeneous linear system has only trivial solution, so for such a linear system, the coefficient must all be zeros. So any linear relation becomes trivial. When any linear relation of columns are trivial, that means that these n columns are linearly independent. Okay, so this is what we learned before. Okay, so the columns of A are linearly independent. So of course, so that the n rows A1T, A2T, up to ANT of AT, okay? So AP is A1T, A2T, etc. Because the method becomes to the n times n. Okay? So A transpose, the n rows are linearly independent. Because any linear relation on the n rows is one-to-one corresponding to a linear relation on the columns. Because you just take the transpose, right? So that we know the columns are linearly independent. Of course, the n rows are also linearly independent. Now, once we know that a matrix has linearly independent rows, now by theorem, important theorem in 1.3.11. Okay? In chapter 1, that the reduced row echelon form say U of the A transpose has no zero rows. So it's going to be F1 has no zero rows. That means that every row of U has a pivot. Every row of U has a pivot. Right? If you go back to look at the theorem 1.3.11, it says that if a matrix, if the rows of a matrix are linearly dependent, then the reduced row echelon form or any row echelon form has a zero row. Okay? Has a zero row. So we use their converse. Their converse saying that because the matrix has linearly independent rows, so when we use the Gauss-Jordan elimination to reach to the reduced row echelon form U, then U has no zero rows. Means that every row has a pivot. Alright, so it's crucial to remember theorem 1.3.11. Okay? Now, so that each row of the U, the reduced row echelon form contains, so each row of U contains a pivot. Okay? Contains a pivot. So now consider, now we are able to solve the linear system here. So now consider unlinear systems. Okay, A transpose xi equal to bi for I from 1 to n. Okay, and where we know bi is just 0, 0, 1, and 0, 0. Okay. Standard unit vector. Okay. So now the associated, so to solve the linear system, the associated augmented matrix A transpose and EI. Okay, so this is also associated augmented matrix. And then by row operation, by elementary row operations, okay, we have the coefficient matrix A transpose will take in the reduced row echelon form. Alright, U and also UI. Okay, so the last column becomes UI. Here. Now. And because that each row has a pivot, so which is consistent. Things. There is no zero rows. In U. So each row has pivot. So that the system must be consistent. Alright, so there is a solution. So now, so there is a solution. So there is a solution, say xi equal to vi, such that A transpose and vi equal to vi. Because it's consistent, so it means the existence of solution is justified. So we have a solution, so we say vi. Okay, and now we find the vi already. So now we will combine them together. So A transpose V1, V2 up to Vn equal to V1, V2 up to Vn. Okay, so this implies A transpose and the D here, or just V here, not using D, equal to identity, where the D matrix is V1, V2 up to Vn. Okay? All right, and then by taking the transpose, so we have D transpose of A. So A, P, D transpose equal to identity. The transpose. This means D transpose A equal to identity. Okay, so we find a reference thus C defined to be the D transpose is left inverse. Okay, and we have that. Okay, so this is my assumption. Any questions? So no questions. Okay, so I'll stop here and we will have quiz number 6. Remember, next Wednesday we will have midterm number 1. And the coverage will be chapter 1 to chapter 3. So I will finish chapter 3 on Friday. Alright? And I will assign the next recommended exercise tonight. Right. So I encourage you to attend the TA's office hour next Monday evening. Okay. If you want to have a good grade on quizzes, I encourage you to go to your TA office hour to ask questions. Because the TA, they are very capable to answer your questions about the exercise problem. Some exercise problem not so easy for you to solve at home. Okay? So I highly recommend you to attend the TA office hour. All right. So good luck with today's quiz.